All right, welcome back to Biostats Lectures. This is Module 7a, and we're going to talk about the binomial distribution. So, um, an example that I'm going to use throughout these videos is this case of, let's think of looking at albinism in mice. We think it might be controlled by an autosomal locus in which the albinism phenotype is recessive, and we know that mice are diploid. That means they have two copies of each gene at an autosomal locus. We're going to cross two mice that are both heterozygotes at the locus of interest. And if this is, this is the type of cross that Mendel did with his peas. If this is a simple Mendelian trait, we'd expect a 3/4 non-albino and 1/4 albino from our cross. Let's say we go ahead and do a small cross and get 4 offspring, and 2 of them display albinism. All right, so this should feel pretty similar to the examples of hypothesis testing and questions that we were looking at in chapter 6. So let's just start going through the steps of how we test hypotheses. Remember, step 1 was state your question in terms of null and alternative hypotheses and choose an alpha for your test. So we're going to use an alpha of 0.05 as we often do. So what about the null? So remember, that's got to be a specific statement about a population parameter, not a sample parameter, or excuse me, not a sample statistic. So we're going to say the proportion of albino mice in heterozygous crosses is 1/4. And remember, the alternative is the hypothesis that's just kind of anything other than the null. So it's going to be the population proportion does not equal 1/4. Okay, we collect a random sample. I said we did that with n of 4, and 2 of them show albinism. Calculate descriptive statistics and the test statistics. So one descriptive statistic is just the number of successes, or we use this term successes when we're talking about binomial trials that have 2 possible outcomes. We just designate one of them a success. It doesn't matter which one. It doesn't really imply that one is better than the other. It's just a terminology for thinking about this kind of problem. So we have 2 mice showing albinism, and the empirical proportion of our sample, 2 out of a sample size of 4, right? The p hat is x over n. P hat is 0.5. So under the null hypothesis, the population parameter is 1/4. Here we have the sample proportion of 0.5. Obviously, there's a pretty big discrepancy there, but it's a really small sample size. So what we need to do next is determine the p-value. That involves 3 sort of sub-steps. What values of the test statistic are expected under the null? So if we're using x as our test statistic, the expectation under the null, that's that funky e there, the expectation of x under the null is the sample size times the population proportion hypothesized under the null. So that's 4 for our sample size and 1/4 for that population parameter. So we'd expect to see about 1 offspring showing albinism. Okay, so we saw 2 instead of 1, so we can see that there's a difference. But the question is, how does that observed test statistic differ from the expectations under the null? We've got to compare the datum to the full null distribution of that test statistic. And then we can calculate the p-value, which is the probability of observing the value of the test statistic that as extreme or more extreme if the null is true. So that's the p-value, and that's what we'll use to decide whether or not we reject the null hypothesis. So in order to do these steps B and C here, we need to have the full null distribution. And so in chapter 6, we just provided the numbers for you. What are all the probabilities for all the outcomes? But of course, when we do statistics in the real world, we don't automatically know what the null distribution is. We need to be able to figure out what it is. So this chapter is about how to figure out what the null distribution is for this type of problem. So remember, the null distribution, it's a probability distribution. It's a distribution where the variable is the test statistic, x in our case, and it's calculated under the assumptions that the null is true. So the full way of expressing this would be something like, what's the probability of some value of x given that we have a sample size of 4 and a population proportion of 1/4. For brevity, I'm just going to say probability of I given the null. And I'm even going to shorten my notation down a little bit more in the coming slides, just so we can fit everything on a reasonable font size here. Okay, so a probability distribution is a probability assignment of every possible value in the sample space. So we just need to start walking through the possible outcomes. You could get 0 mice with albinism in your cross. What's the probability of that happening? In order for that to happen, the first one is going to have to be 0, so that's no for albinism. The second mouse is going to be 0 for albinism. So I'm using 0 to be non-albino and 1 to be albino. So all 4 of them will have to be non-albino mice. So what's the probability of that? Well, under Mendelian genetics, different gametes and different zygotes, they should be independent because that's the way that he observed his pea plants behaving, and we now know that's because of the way meiosis works, that these should all be independent probabilities if we've got a simple trait. So that means we can just multiply these four probabilities together, the probability of each one of them. And, based on the null hypothesis, the probability we'd see a 0 is 0.75 because the probability of seeing an albino mouse is 1/4. So the probability of not seeing that in one trial is 0.75. So 0.75 to the fourth power, and that's this number here, almost a third probability. Okay, so that's how to calculate the probability that we see 0 mice with albinism in our cross of 4, if the null were true. What about what's the probability that the first one displays albinism, but not the second one, and not the third one, and not the fourth one? Once again, that's another and statement, so we can do that theme multiplication. Probability of the first one being 1, but the next 3 being 0. I'm going to further shorten my notation to that 1, 0, 0, 0 for this sequence. So it's basically that order of those 4 offspring, just so we have a tertiary notation here. So what is the probability of that? Well, it's the probability of the first one being having albinism, that's 1/4, and the next 3 not. So 0.75 raised to the third power. And that's 0.105. It's 1/3 of the previous number because instead of multiplying by 0.75, we're multiplying by 0.25, which is a third smaller. Okay, but the crucial thing to realize is if we want to know what's the probability that we see one offspring with albinism, that's not the same thing as this probability that we just calculated, right? Because we've seen this before in the probability chapter, there are more than one ways of having x equals 1 here. This is just one possibility. So to get one offspring with albinism, we could have the first one with albinism, the second one, the third one, or the fourth one. So each of those possibilities is joined with or, so we should add up each of those probabilities. Once again, those are mutually exclusive outcomes because they can't happen on the same trial, so we can just do the simple addition rule. And we should also note that by independence, these are all equal to each other because it doesn't matter what order the mouse with albinism is relative to the other ones because each of the offspring is assumed to be independent and a simple Mendelian trait. So each one of these numbers should be that same number, 0.105, et cetera, et cetera. So that means we can just count up how many there are. There are 4 of them, 4 possibilities, 4 times the probability of any one of them, 4 times that probability. And now we're up to a probability of 0.42 for that. And it makes sense that that's a higher probability than the probability of seeing x equals 0 because we would expect to see about 1. We already calculated the expectation under the null and it was 1, so that should have a pretty high probability. Okay, what about the probability that we see 2 albino mice out of 4 trials? So probability of 2 given the null hypothesis. Well, there's more ways of doing this. We can have the first 2 be albinistic, the first and the third, the first and the fourth, or the second and the third, the second and the fourth, or the last 2. Those are all ways of having 2 mice with albinism and 2 mice that are not albinistic in a subset of 4, in a sample of 4. There are 6 of those. By the same logic, they're all equal in probability, so we can just calculate the probability once. So it's 6 times the probability of the albinism squared, because there's 2 of them, and non-albinism squared, because there's 2 of those as well. So you do the math on that, and you get down to 0.21. This is getting pretty tedious, right? We have to think about all the ways of mixing these things and then calculate these probabilities. And it's sort of tedious, particularly to do this step, making sure that we haven't missed anything or double counted anything. But let's just continue here. The probability that x equals 3. This is starting to look a little easier again because there's only 4 possibilities, 4 places that the non-albinistic mouse could be. The 4th position, 3rd position, 2nd position, or 1st position. So there's 4, and that's 0.25 to the 3rd power because 3 mice show albinism, and 0.75 just once. So we get that probability. And the probability that all 4 of them show albinism, there's only one way to do that. One's on each trial, so the coefficient is 1. We have 0.25 to the 4th power, and that's this small number here. Of course, we usually look at probability distributions in a graph, and I'll show you that in a second. Here is the full probability distribution laid out in a table. This is another way of looking at a probability distribution. Certainly when there's a small sample size, this is appealing, not when there's a large sample space. Okay, So these are all the probabilities, and we should note that if we add them up, we do the summation here, we get a probability of 1, so that should be comforting to us because the probabilities have always got to add up to 1 when we're talking about all of the mutually exclusive options. So that's all the calculations we just went through. It was a fair amount of work. And this is what the probability distribution looks like. There's our expected value, which has the highest probability associated with it, but all the others have some probability. And even having 4 mice with albinism is it's not infinitesimal. It's a visible bar here at least. So remember, if we were thinking about this is the null distribution, what's the p-value? The observed value in our data set was 2. So we want to think of things that deviate from the null expectation by 2 or a more extreme amount. And remember, we can also consider the other tail of the distribution. 2 is 1 step greater than 1, so maybe we should consider 0 as well. There are some arguments by statisticians that you should only consider entries here where the probability under the null is lower than the observed data. Since 0 is a higher probability, we wouldn't exclude it from the p-value. But we're not going to get into those complicated ways of doing this binomial test. We're just going to use the distance from the expected value as our way of deciding which part of the tail gets colored in. So here's the p-value shaded in, not with my horrible job coloring it in with my pen, but using R to program that. We can see it's a pretty appreciable p-value, all right? And so remember, once again, the way we actually calculate the p-values, we figure out all of the outcomes that contribute to as extreme or more extreme than the observed outcome. That was the observed outcome. 3 would be even further from the null expectation. And we also consider the other tail that's equally extreme on the other side and going further to the left. Now, there's nothing further to the left than 0, so we only have one term over here. In this case, there's only one value that's excluded, that expectation. So it's actually easier to calculate this by just doing 1 minus the probability of 1. So we can use that probability trick, and we can get this probability for our p-value, right? As opposed to looking up the 4 values that we calculated for these numbers, we can just use the subtraction rule. But either way you do it, you'll get a p-value of 0.578, which is quite large. Remember that step 5, make a decision about the null hypothesis. If the p-value is less than our alpha, then we reject the null. If not, then we say that we do not reject the null. In this case, the p-value was about 0.578. It's much larger than 0.05, which was our alpha value. That's sort of our default alpha value. So that means we do not reject the null, that the p is actually 0.25. Now this, of course, being the population proportion p, remember that's completely distinct from the p-value. It's just unfortunate that we have to use both of these, but that's the tradition in statistics, to use the population proportion as a little p. Okay, so then it's also important to be able to state this, answer the question, and report the results in English. And we need to include a lot of information in that. So in a study of 4 offspring, there's our sample size, from a dihybrid cross, that's the name of this heterozygote cross, 2 of the offspring, p hat of 0.5, displayed albinism. The deviation from the expectations of 1/4, there's the null expectation, showing albinism was small enough to be explained by sampling error, p-value equals 0.578. That's one way of saying that it was not significant, right? It could be explained by sampling error. We don't need to think that the null is, we don't necessarily have reason to think we should reject the null. You could also say something like, this was not statistically significant difference from the expectations of the model. But remember, we're attaching that p-value to where we're making the statement about statistical significance, because this is how we're deciding on statistical significance. Okay, so that should feel a lot like what we did in Chapter 6, except here we had to do a lot of calculations that we didn't have to do in Chapter 6. But it's also nice because now we can solve problems where someone's not just giving us the probabilities, right? Now let's go back to the table of probabilities that we used and look a little bit about how they were arrayed out there. So these are all the equations that we used for calculating these probabilities. And we can see, for one thing, we can see the exponents. They always add up to 4 because there were 4 offspring in the trial. And so they could be 0 albino and 4 non-albino, or 1 versus 3, or 2 and 2, or 3 and 1, or 4 and 0. So we can see that we get the full sample space here in terms of our x value. And over here, we have our sample size minus x is the exponent for the other probability. So that's a pattern that we can pick up on. We've got some coefficients here. We're going to talk about those in a little bit. So what we can say, what we can extract from this is the probability that we have x successes on n trials with the proportion of successes per trial of p, probability of p, is just some coefficient we're going to talk about in a second, and it's going to be the success probability raised to the number of successes that we're interested in, and the failure probability raised to the number of failures that we had. And so these two exponents should always add up to n. One of them is going to be x, and the other one's going to be n minus x. Okay? So that's a pattern that we can notice, and it'll be helpful to remember this formula and how to use it. What is this b in x? That's what's called the binomial coefficient. We're going to talk about it in just the next few slides. We call it a coefficient because it doesn't depend on the value of p here at all. Because the binomial coefficient shows up in lots of parts of math unrelated to probability, and using this x variable, it's often the case when talking about the binomial coefficient we use k for the number of successes. So you'll frequently see it written this way, where we've just swapped in k for every place that x occurred. So when we're talking about the random variable x, it's totally fine to write the formula like this, but in general you'll see it more commonly in terms of k in NP. Okay, so what is this this coefficient? You've already heard me call it the binomial coefficient. It's binomial because there's two choices, right? A success and a failure on each trial. And remember, it doesn't really matter what we call a success or a failure in any kind of judgmental way. It's just arbitrary. So in this case, we were calling albinism a success. So what does the binomial coefficient do? It was counting how many distinct sets of k items you can choose out of a set of n items. So that's what we were looking at, how many ways we could get, 2 albinos out of 4 offspring. How many ways to choose 2 different offspring from a set of 4, for instance. That was one of the coefficients. So it's this counting operation for how many ways of doing this ways of having this number of successes there are. So the binomial coefficient for n and k is denoted with this funky, it looks like a fraction, but there's no bar in the middle, so it's just parentheses around an upper number and a lower number, and that's pronounced choose. We call this n choose k. Okay, so it's a little bit of weird notation. Make sure not to put that bar in there so it doesn't look like division. How do we calculate it? Well, in order to calculate it, we need to remember how to do factorials. So you probably learned factorials at some earlier math class. The factorial of n is denoted in exclamation point. And it's like n times n minus 1 times n minus 2, all the way down to 2 and 1. So you do that full product, right? And so it's a series of multiplication events. Now there are a few little weird corner cases that we have to cover. The factorial of 0 is defined to be 1, and this is odd because it looks like if you multiply 0 times something, you should get 0. But it turns out this simplifies a lot of our notation if we just consider 0 factorial to be 1, so don't get tripped up by that. Whenever you see 0 factorial, you can just substitute a 1. 1 factorial is just 1 itself. 2 factorials, 2 times 1, that's 2. 3 factorial, now we're starting to see the real pattern that emerges and generally holds. That's 3 times 2 times 1, so that's 6. 4 factorial, 4 times 3 times 2 times 1, it's 24. 5 factorial is 120. 5 times 4 times 3 times 2 times 1. And 6 factorial, we can tersely write that as 6 times 5 factorial. There's this sort of nesting structure where it's always just adding one more factor in front. And so now this is up to 720. So one thing to notice is these numbers grow really quickly from 120 up to 720 is a big jump, and then you go to 7 and you'd be up to somewhere around 5,000, and 8 factorial is something like 40,000. So it's a really fast growing function. Okay, so that's the factorial. We were asking on the previous slide, how do we calculate n choose x? N choose x is defined to be n factorial over k factorial times n minus k factorial. So you use this factorial function 3 times here. Up on the top goes the sample size. On the bottom is the product of the number of successes factorial and the number of failures factorial. Okay. So what frequently happens is if we sort of expand what's going on here, we'll see tricks like this in the next few slides. So I just want to pause and talk about it. There'll be some initial terms, n times n minus 1 times n minus 2, etc., down to some n minus k minus 1. And then n minus k factorial is what is the rest of this. So you don't always have to write all the terms of n all done to 1. You can substitute with another factorial. And then on the denominator, you have k factorial and n minus k factorial. So these will be able to cross out. So frequently, the efficient way to calculate that is going to be just multiplying k factors up here, starting from n, working our way down, and k factors down here, starting from k, working down to 1. And that's usually the efficient way to calculate this number because a lot of this will cross out. So this is the correct definition. This totally works, but sometimes your calculator will run out of memory and won't be able to calculate that, and this method down here will work. And we'll see this in several examples. Okay, so don't get too bogged down. It'll make more sense when we walk through a real example here. Here's back to our table again. Remember, we're talking about this coefficient out here that I was abbreviating b n comma k, the binomial coefficient. So that's what we're highlighting here, this part of the equation. So the first one is 0 successes. So 4 factorial over 0 factorial, and then 4 minus 0 is 4 factorial. And we get some crossing out. 4 and 4 factorial, so we just get one possibility. What about 1 success? Now it's 4 over 1 factorial, and 4 minus 1 is 3 factorial. So once again, we get some crossing out, and we just get 4, right? What about 2 successes? Now we're not having to think about, let's list them all and count them up. It's just we can use this formula, which turns out to be easier. So it's n factorial over k factorial and n minus k factorial. So 4 factorial over 2 factorial and 2 factorial. 4 times 3, the 2 factorials cross out here. So 4 times 3 is 12, divided by 2 is 6, okay? And then down in the bottom, we have 4 factorial, 3 factorial over here, and 1 factorial. And so now the easier thing to do is to cancel out this k factorial with 4 times 3 factorial, so that cancels out, and we end up with just 4. So we see often we don't have to do as many steps as the factorial notation implies because there's a lot of canceling that goes on here. And once you get the hang of it, it can be not too tedious to calculate. Okay, so that's the full table. So now we've just described how to calculate all the values for the binomial distribution, and we've walked through all the pieces of that formula. So the binomial distribution itself is the probability of k successes on n trials with p probability of success on each trial. So that shows up in a lot of contexts because if we set up a random sample of n independent trials where they're truly independent, then because our samples are independent, because they're drawing from some process that we're interested in studying, they should have the same probability p of success on each trial. So when we've got a binary outcome, it could be red or black, or albinism or not, yes or no. There's only 2 possibilities. Then we can think about calling one of them a success and say, let's just count up how many successes happen. And we've got our sample size n. They've got to be independent in order for this to work, and they've got to have the same probability for each one of them. But we can use this binomial distribution, and we can calculate the probability of any outcome that we want using that formula that we just went through. So here's the formula again. I know it looks a little intimidating, but as we work through another example, you'll hopefully see how this all fits together, and it's not too bad once you learn the basic tricks, and a little repetition will help with this. So remember, it's this binomial coefficient, n choose k. It's the probability of success raised to the number of successes you're interested in, so p to the k, the probability of failure raised to the number of failures you're interested in. And so there's some nice tricks you can use to double check yourself. This is always n factorial in the numerator. This exponent for p, that's going to be over here in the denominator of the choose function, and here's the number of failures. That should also show up here. So there should be some nice matching here, and you can double check that you're not sort of getting off on the things that you're supposed to be calculating at each step. Okay, so that's the basics of the binomial distribution. In the next lecture, we'll talk about how to use it a little more and how to do some confidence intervals and things like that. All right.